Well, welcome back, colleagues. We begin Module 5, in which we shall examine the difference in two means. You will recall that in Module 4, we introduced the concept of testing a hypothesis, testing a claim, using, of course, a six-step plan. And this six-step plan is very important for you as you move forward in many of the tests that you're doing. The first thing that you do, you state the null hypothesis. You state the alternate hypothesis, you establish a critical value, you find a test research statistic, you draw a conclusion, which is reject or fail to reject, and then you write your findings into statements. Now, keep in mind that in this situation, with testing between two means, we're not going to be calculating a lot of values by hand. What we're going to be doing is taking sample sets. We're going to put them in SPSS, and using SPSS, we're going to run a difference of two independent means, and we're going to get a test readout, and we're going to interpret that readout. This is going to be a little bit easier than you think it is, but you have to learn how to use SPSS statistical software. SPSS stands for Statistical Packages for the Social Sciences. The good thing is that SPSS is available with production of your student ID for a very, very, very reasonable price, less than $90 for a year's license. I want to remind you that the investment is actually worth it because you're learning a very sellable skill set when you can run SPSS, and there's a lot to learn with it, but we're going to start easy and we're going to do a differences of two means. Now, there are some thoughts that we want to utilize the structure of hypothesis testing to examine the claim. You remember that we rejected or failed to reject the claim. That was our decision, but we had one population. Suppose we want to compare two populations to determine if they are similar, if they differ. Here's a problem, and then we're going to talk about this problem. Consider the problem. The deflection temperature under load for two different types of plastic pipe is being investigated. Two random samples, n equals 15, are tested, and the deflection temperature observed are reported in degrees centigrade. Now, deflection temperature is the temperature at which the pipe yields under a given weight. As the temperature gets hotter and hotter, at what point does the pipe bend? Does the deflection temperature for type 1 pipe exceed the deflection temperature for type 2? That's going to be our idea. Heat deflection temperature is defined as, this is the scientific definition, it's defined as the temperature at which a standard test bar deflects a specified distance under a load. It is used to determine short-term heat resistance. Now, what that means is we put the pipe under a weight, we increase the temperature, and at what temperature does the pipe yield? It distinguishes between materials that are able to sustain light loads at high temperatures and those that lose their rigidity over a narrow temperature range. Our test procedure, the bars are placed under the deflection measuring device. Now, this is just telling how they would do it in industry. A load of 0.45 MPa or 1.80 MPa is placed on each specimen. The specimens are then lowered into a silicone oil bath where the temperature is raised at 1 degree centigrade per minute until they deflect 0.25 millimeters for ASTM, 0.32 millimeters for ISO flatwise, and 0.34 millimeters for ISO edgewise. Now, all that's doing is telling you how we're going to test it. Now, here's the good news. Here's the two pipes. They want to know if type 1 pipe has a higher deflection temperature than type 2 pipe. The interesting thing may be brought on by the problem. Maybe type 1 is more expensive than type 2 pipe. And the purchaser wants to know, well, is it better? Does it have a higher deflection temperature that would warrant the increase in cost? Well, the way we handle this is we take a sample of type 1, a sample of type 2, and we compare those two samples to see if there's a difference between the two populations. Now, here's what a sample might look like. We have 15 values for type 1 and 15 values for type 2. Now, before we proceed in how to do this problem using software, I want to remind you not to panic. You may not grasp the scientific terms of what deflection temperature is and all of that. But what you can do is you can compare two samples, and that's what I'm going to teach you how to do. Notice that the samples were small samples. If we were doing this by hand, we would be doing tables, and we would be understanding that we're using a t-score from the t-score table because they're small samples. Now, go back to the hypothesis test just a minute. We have 6 steps, and can we utilize this model using software to do these 6 steps? And the answer to that is certainly. What we're going to do is called a t-test. Now, I want to explain that to you. It is not because we have small samples that it's called a t-test. Now, distinguish between a t-score, which is a critical value, a t-statistic for a small sample where you have a set level of confidence and you have so many degrees of freedom. This is called a t-test, which is something completely different. That's a short name for comparing two populations. If we want to compare two populations and those meet our terms, then we're going to conduct a t-test. Here's the important considerations. Are the two populations independent? Does the deflection temperature of one affect the deflection temperature of the other? And the idea is they certainly don't. They are independent samples. Independent means one does not impact the other one. The other idea is, are they normally distributed? And later I will show you how to determine that, but what you're really going to do is you're going to find values called skewness and kurtosis. Skewness means, does the curve go to the left or does the curve go inordinately to the right? Kurtosis means, is it too sharp or is it too flat? If you'll think just a moment with me about a normally distributed curve, it is centered, and then it goes up to kind of a set height. It's not too sharp and it's not too flat. These values, skewness and kurtosis, when we run them, we must have an absolute value less than 0.3, or less than 3. That means they were, to be approximately normally distributed, they need to fall between -3 and 3, and I will show you how to do that with a table. And are the variances of the populations equivalent? Now, it's very important that we have what we call homogeneity of variance. Homogeneity of variance means that the curves look somewhat alike. They're approximately the same. And one's not spread real wide and one's spread real narrow, and then we're trying to compare them where they have different variances. And homogeneity of variance, what does variance refer to? It refers to standard deviations. Are the standard deviations of the curves approximately the same? You remember that variance is the square of the standard deviation. Now, again, I remind you, back in the days when they didn't have calculators and they were using these squared values, it was difficult to find the square root. You had to go through a procedure. I remember when you took a logarithm of the number and you cut it in half and you looked up what value it was. We don't want to do that. We're going to find something called homogeneity of variance, which is going to tell us either the variances, meaning the standard deviations, are approximately the same or they're not, and we will learn how to run the data. Now, I don't want you panicking yet. You've got this. This is not any more difficult than anything else. And actually, you're going to find that it's a lot easier because you're going to put these values into software. We're going to run the software, and the software is going to produce a result that you're going to have to interpret, and I will show you how to interpret that. It's really not very bad. You've got this. You're clever.